Hello everyone. This is part 6 of presentation made on module 2 data communication. So we were already discussing the properties of transmission media, different transmission media, particularly the guided transmission media, twisted pair and coaxial cable. We completed, and then we started discussion on fiber optic media. So out of the three guided transmission media we are having, the fiber optic is the one which is providing the maximum performance, but it's costly at the same time. Now let's move on to the transmission characteristics of fiber optic. We are continuing in that discussion. So fiber optic, it's a cable enables the transmission of very high speed voice, video and data traffic in enterprise and service provider networks. So optical fiber transmits a signal encoded beam of light by means of phenomena called a total internal reflection. Now, total internal reflection can occur in any transparent medium that has a higher index of refraction than the surrounding medium. So we have a property called refraction index. So that is a property of a medium. We will see how to define that. So no need to understand that much. Just understand what is the principle behind it. But if you look on to this refractive index and all in detail, that will complicate things. So just have a rough understanding about it. So with respect to that particular property, refractive index, this total internal reflection is happening, and that we will see how it is to be defined and how it is happening. Now the criteria is like the medium where the total internal reflection is occurring, that should be transparent, and at the same time the refractive index of that medium where that total internal reflection is happening should be higher compared to the surrounding media. So accordingly we will be constructing the fiber optic cable, and we have already seen its structure where we have that core covered with the cladding. So definitely through that core we will be passing that light beam, which will be for which this total internal reflection will be happening, and that time the refractive index of that core should be higher compared to the surrounding medium, which is that is nothing but the cladding. So in that way we will be constructing it. Now in effect the optical fiber act as a waveguide for frequencies in the range about 10 raised to 14 to 10 raised to 15 hertz. So that's a typical bandwidth or spectrum of means range of bandwidth or spectrum of optical fiber where it is working, and we know this covers the portion of the infrared and visible spectra. And I think at the beginning of this module we saw that electromagnetic spectrum, and where we saw where that visible spectrum is coming, everything. And so visible spectrum is typically coming in this frequency range, and over which our fiber optic cable is functioning. Now if we are looking at the total internal reflection phenomena, it is the complete reflection of a ray of light within a medium such as water or glass or any other such transparent medium from the surrounding surfaces back into the medium. So the signal will be trying to hit the surrounding, and it will reflect back into the same medium. So like that the light will be moving towards the end. Now the phenomenon occurs with a condition, and that is that you have to note down, where the angle of incidence is greater than a certain limiting angle called a critical angle. So we will see what is this critical angle. So critical angle of incidence is the angle at which the signal is incidenting on that means that area where this core and cladding are meeting. So when the signal is the particular light wave is incident on that particular interface, that area, the angle at which it is incident called angle of incidence, that should be greater than a certain threshold value, and that is what we call as a critical angle. After this critical angle, if we are able to make the light beam incident in such a way that the angle of incidence is greater than the critical angle, then only we are able to reflect the light back, so that the total internal reflection is happening. Now, in general, the total internal reflection takes place at the boundary between two transparent media. This is what I am trying to say, because when a ray of means we have that boundary between that core and cladding in case of fiber optic media. So when a ray of light in a medium of higher index of refraction approaches the other medium at an angle of incidence greater than the critical angle, this will happen. That is so that incident area is a boundary between the two transparent media in our optical fiber, the core and cladding. So for a water air surface, the critical angle is typically 48.5 degree. That depends on the type of media. So if we are looking at water and air, within water, to for this total internal refraction to be happen, the angle of incidence should be greater than this 48.5 degree. So similarly for other surface, that value will vary. So because in indices of refraction depends on the wavelength of the signal, the critical angle and hence the angle of total internal reflection will vary slightly with the wavelength and therefore with the color. So now let's see what is this refractive index. It is a measure of the bending of a ray of light when passing from one medium into another. And so whenever a ray of light is passing from say air to water or water to some other surface like that, when it is moving from one medium to another, the how it is bending, the measure of that bending of that particular ray of light is called a refractive index. So we can formally define it like this. Refractive index N is defined as a ratio of the sine of the angle of incident to the sine of the angle of refraction. So we already seen the angle at which it is the light is incidenting on that surface. Take its sine value to the angle of refraction. So once it is reflecting, with what that refraction happening. So sine R. Where I is the angle of incidence of a ray in vacuum. So so when we define this term, we will be assuming that the outer surface is vacuum. With respect to vacuum as outer surface, what is the refractive index of a given medium? That given medium can be air, water, glass, whatever it is. The outer interface, we are assuming that is vacuum. So with respect to vacuum, what is the angle of incidence? Which is the angle between the incoming ray and the perpendicular to the surface of a medium. So we are going to calculate the refractive index of a given medium. Take the perpendicular to the surface of the medium, that is nothing but the normal of the given medium. With respect to that normal, what is the angle of the incoming ray by which it is incidenting on the medium. So at that incident point, take the normal and measure the angle between these two. Now angle of refraction is the angle between the ray in the medium and the normal. Now angle of refraction we are calculating with respect to the medium. Angle of incidence we are calculating with respect to the vacuum. So just like that is listed in the next slide. So we will see that. So it is something like this. So here we have a given medium. It could be air, glass, whatever it is, and outside we assume that it is vacuum. And just like so here we have the medium and here it is vacuum. Now from vacuum a particular light wave is incident on the medium. So and it is getting refracted like this. Now how we will be calculating the angle of incidence? Take the normal to the medium. The angle between these two is called a refraction, the angle of incidence. And similarly, when it is refracting, again for the medium, towards the medium it is refracted. So for the given medium, the angle between that the refraction of the light and the normal to the medium, something like this. So this is the angle of refraction. So take a sine of I divided by sine of R, that will give you the refractive index of a given medium. Now we can also calculate it like this. That is, refractive index is also equal to the velocity of light, that is c. We know the standard value 3 × 10 power 8 meter per second of a given wavelength in empty space divided by its velocity v in a substance. So in empty space, what is velocity of light? The standard value divided by the velocity of that particular. So also velocity of the v of the same light in a given medium. So we are going to calculate the refractive index of a medium. So what is when we are transmitting a light wave through that medium, what is the velocity in which it is traveling through the medium, that is v. And when it is in empty space, what is the velocity by which the light is moving, that is c. So take c by v, that will also give you the refractive index. So anyway, just have a brief idea about it, no need to look into the term in detail. So we have a property called refractive index, and we can calculate it like the ratio angle of incidence divided by sine of angle of refraction, or the velocity of light in empty space divided by the velocity of light in the particular medium for which the refractive index is calculated. So with respect to this refractive index, we can see whether the total internal reflection is happening or not. Okay, so for it to happen, the medium on which the light is that is a core, we are transmitting the light should have a refractive index that is greater than the surrounding. Okay, then only we can make the light undergo that total internal reflection. So that about the phenomena. Hope you got an idea about it. So this is the basic principle in which the optical fiber is working. So they may ask you a question on that, what is total internal reflection. That time you can define it, and you can say, briefly describe what is that refractive index. And we had another term called a critical angle. So that is a benchmark like that. So whenever that angle of incidence is greater than the critical angle, the total internal reflection will happen. So that is again a property, and those things are having rigorous proof and all. We are just looking at the property only. Okay. So further details and types of fiber optic, everything we will see in the subsequent video. Thank you.